Nuclear power to get us to Mars, clouds that are kind of on fire, and a vaccine for the plague, maybe. These are all the things that have caught my attention this week in science and technology. I'm not going to tell you that the plague is back, because honestly it never really left. You might have learned about the plague in school in history class as the Black Death, a plague pandemic that ripped through Europe in the 1300s. Human cases today are generally in the single digits, but plague is a zoonotic disease, and that means it's caused by germs that spread from animals to people, and that means that there's always a reservoir of it out there in the wild. Plague is the disease caused by Yersinia pestis, a bacteria, and you know what that means. It means that we can use so if it's caught in time and correctly diagnosed for what it is, then the prognosis is pretty good. But what about a vaccine? Because if we use too much, then we risk increasing antibiotic resistance. A vaccine could just update the antivirus software of people who live in areas that are high risk, so that if they're exposed, their body can start defending itself immediately. Plague actually had one of the earliest types of vaccine called the inactivated vaccine, so called because it contains bacteria that are already not alive, and as a result they can't replicate and produce a real infection, but the immune system will still respond and it will remember what they look like, so if it sees them again then it will just jump on it. Inactivated vaccines don't produce as much of an immune response to the pneumonic plague, unfortunately. The pneumonic plague affects the lungs, and as a result we use live attenuated vaccines, where you take an infectious agent and alter it so that it's either harmless or less virulent, but it still trains your immune system to jump on it. So, 2 new live attenuated vaccines have shown real promise in early tests in mice, and what that means that among all the mice tested, all the ones that received the vaccine survived exposure to the bacteria. Even more exciting is that these vaccines show promise against the pneumonic plague, which affects the lungs. The vaccines are only at the beginning of a long and arduous journey. They'll need to pass tests in primates and then humans, but if we can end up with a vaccine for the plague, then not only can we protect people who live in areas where they're particularly exposed to it, but we can also have it in our back pocket if it ever decides to go for it again and try and become a global pandemic. Nuclear craft for interplanetary travel. That's NASA's pitch for a new type of spacecraft that might be able to get us to Mars faster. The nuclear part is a fission reactor. Uranium atoms undergo fission, which releases heat that warms a fluid. That fluid spins a turbine and generates electricity. But how do you turn electricity into propulsion? Newton's third law means that if we want to go faster in space, then we have to throw something overboard. Usually this is exhaust gases from burning rocket fuel, but the SR-1 Freedom is going to be powered by electrical energy once it's in space. Enter the Hall effect thruster, and no shade to regular rockets, but this does look an awful lot more sci-fi. The Hall effect thruster is genius because instead of throwing out a lot of stuff very quickly, it throws out a small amount of stuff at ludicrous speed. For comparison, a combustion engine has the kind of thrust that would be able to shift like a bus, but a Hall effect engine has the kind of thrust that would be able to lift like an apple, maybe? And you might say to yourself, what? Why would you choose that one, not the fast one? The answer is because we're talking about engines to use once the spacecraft is already in space. It doesn't necessarily have to be powerful enough to lift it off of Earth. A regular combustion rocket will do that. So in space, in a vacuum, a Hall effect thruster can work if it runs for thousands of hours. So it does. Normal rocket engines use a fuel and an oxidizer, combusting them together to release the energy stored as the chemistry of those propellants, and it produces a short but very powerful thrust. It's amazing to see, but it's not the most efficient thing. But an electrical propulsion system uses electrical energy, and as a result it means that you can do away with a lot of the needs and limitations of hauling around combustible propellant. So in a Hall effect thruster, electrical energy is used to positively charge or ionize xenon, the propellant, and then a combination of electrical and magnetic fields accelerate those ions and shove them out the back, providing thrust. So in a Hall effect thruster, the energy is not stored as the propellant, it is imparted onto it. So a Hall thruster is more like a big candle burning away with a tiny flame for a very long time, whereas a regular chemical rocket is more like a hand grenade. Because there's no friction in space, both of these methods are not just moving the craft forward, they're accelerating them, and over the course of 300 days from Earth to Mars, for example, that can really add up, and hopefully in the future we can use this for long distance space travel. The opinion of NASA is that it could reduce the amount of fuel or propellant needed by up to 90%, saving millions in launch costs, which sounds great. We'll see when it launches in 2028. We've all heard the adage that every dark cloud has a silver lining, but what if it was just on fire because of climate change instead? This is pyrocumulonimbus, and it's a type of cloud that forms over a source of extreme heat like a nuclear explosion or a wildfire. As climate change continues, global warming means that the surface of the Earth is getting hotter and hotter, which means wildfires that are natural and happen every year last longer, there's more of them, and they're harder to put out. You've probably seen about the wildfires that have been happening in France at the minute, but one thing that you might not have known is that wildfires in France have resulted in pyrocumulus clouds. Those pyrocumulus clouds have generated lightning that have started more wildfires. These aren't a new phenomenon, but what happens is the immense heat causes smoke and ash and, importantly, hot embers to be pulled up into the cloud, and those can be sent anywhere around the surrounding area, which makes it even harder to put out. Whilst it is very fascinating, there's no neat bow that you can really wrap around all of this. It's a horrible event and terrible for the people who live there, and it's going to keep happening because as climate change continues and the globe keeps heating up, it's going to get worse, and I don't know what we're going to do about it. And that was This Week in Science and Technology. Thank you very much for watching. If you thought I missed something, leave a comment and maybe I'll cover it next week. But until then, leave a like if you liked the video, subscribe so you don't miss the next one, and I'll see you next week in Science and Technology. That's the show. Bye!